It's summertime in California. People go about their business unaware of what's happening in the skies above. Without any warning, a colossal fireball rockets down from space like a speeding bullet. Upon impact, apocalyptic destruction will ensue. This is not a real-life event, but it could be. At the University of Arizona, planetary scientist Jay Malash and his colleagues have developed an interactive website for estimating the consequences of asteroid and comet impacts on Earth. Web users can actually create their own doomsday scenarios.
Every time impacts were in the news, I'd get call from reporters, and they would want to know what would happen if a certain size impact occurred. I realized that this could all be put in a website so anyone could answer these questions themselves.
Web users can recreate actual chilling impact events. Even the massive one in the Gulf of Mexico that triggered the mass extinction of the dinosaur over 65 million years ago.
Let's suppose that the dinosaur-killing impact occurred not in Yucatan, but in Los Angeles. And we're living in San Francisco, and we want to find out what happens.
In order to simulate the impact event in Los Angeles, Malash enters the following data: projectile diameter, impact velocity and angle, target type, such as water or rocky surface, and distance from the impact.
The computer program will now tell us what we feel here in San Francisco. Calculate effects. As far away as San Francisco, we can see this huge fireball that develops over the impact site. The energy is bigger than all the world's arsenals of nuclear weapons combined. As a result of this impact, Los Angeles is completely obliterated. Next, rock debris blasted out by the impact travels ballistically above the atmosphere and then re-enters over our location. San Francisco will get fried and then buried by 24 inches of debris. Highway trusses will collapse. Multi-story buildings will collapse. San Francisco will not be a good place to be for an impact this big.
This interactive website may seem like a video game of Armageddon, but it's actually serious science and serves as a warning about how dangerous asteroid and comet impacts could be.
This isn't a cartoon or play simulation. The impact effects are all compiled from things like nuclear weapons manuals, by experience from earthquakes, and so we've done the best job we possibly could with all of the best modern technology to get an accurate description of what happens.
Throughout Earth's history, asteroids and comets have been messengers of death. At the same time, they may also have been deliverers of life. Approximately 4.5 billion years ago, our solar system looked like a cosmic shooting gallery as celestial rocks collided and coalesced to form planets. After our solar system was formed, space rocks that didn't mold into planets or moons became wayward debris. Within our inner solar system, millions of these leftover rocks became part of the asteroid belt that orbits around the Sun between Jupiter and Mars.
We think that the powerful gravity of Jupiter was strong enough to prevent these planetesimals from sticking together to form even larger objects that we would consider a real planet. So the asteroid belt, you might think of it as a collection of failed planets.
Asteroids are typically irregular shaped and pitted with impact craters. They range in size from tiny dust grains to hundreds of miles in diameter. Because they were formed at the same time as Earth, asteroids contain the same basic elements we find on our planet to build things. Research scientist Amy Mainzer has located cosmic material in a helicopter factory.
The components of this helicopter here are actually shockingly similar to the elemental constituents we find in all different types of asteroids. The steel struts and the steel engine block, which is mostly made of iron, and say the fiberglass panels, mostly silicon and oxygen, and the aluminum sheeting. Also, some asteroids are similarly differentiated, where you have a metallic iron-nickel core surrounded by a layer of silicates and various combinations of other materials in the shell. When the final assembly of this helicopter is complete, just like the asteroids, it moves. Just as helicopters transport people all around our planet, asteroids and comets transport material throughout our solar system.
Asteroids are cosmic fingerprints that reveal missing clues about Earth's past. Fragments of asteroids that actually survive an impact with the Earth's surface are called meteorites. Most have been recovered in dry deserts or polar regions, where these dark rocks are easier to detect. At NASA's Johnson Space Center, scientist Michael Zelensky has collected and analyzed meteorites.
There's more than 40,000 meteorites been brought back from Antarctica. These are two meteorites, and we think they're from asteroids. Right here, this is a carbonaceous chondrite, and this is an ordinary chondrite. These are the most common kinds of meteorites that fall to Earth today. And they contain a lot of iron, magnesium, silicates, things you see in the Earth. So the asteroids tell us about the earliest history of planet building. Here we have little laboratories for studying how planets evolved early in their history.
And asteroids aren't the only remnants from the formation of planet Earth. In the frigid outer solar system, leftover rocks now orbit neatly in the Kuiper Belt, just beyond planet Neptune.
We believe in the outer solar system, ice and dust accumulated together into a large number of smaller bodies whose orbits were disturbed by the giant planets, and they were eventually scattered out into what we now call the Kuiper Belt.
In the past, the main idea was the comets formed farther from the sun. Because of that, the comets retained a larger amount of volatile elements, ices and frozen water and frozen carbon monoxide, things like that, and more organics. And the asteroids as a whole had fewer of those things.
These icy bodies are not only located in the Kuiper Belt. The forming sun flung comets to the outer reaches of the solar system, which created a spherical deep freeze reservoir known as the Oort cloud.
The Oort cloud is up to a couple of light years away from the sun. Strangely enough, even though the Oort cloud is farther away from the sun than the Kuiper Belt, we think that it may have actually formed inside the inner parts of the solar system. In fact, the reason for this is that some of the materials we find inside comets could only have been formed with high heat. So today, we are building a comet. We're going to start off by pouring the water into the bowl. The water is used because comets are made up of water ice. So we start off with some water. The next thing we're going to add is a couple of teaspoons of dirt. Comets contain a lot of dirt, actually. Dirt consists of various minerals of different types containing all kinds of heavy elements such as iron. Next, we're going to add a little bit of corn syrup. Corn syrup here consists of carbons, hydrogens, and oxygens that we find inside of comets. Next, we're going to add some of this window cleaner. One of the main ingredients inside this window cleaner is ammonia, which is another common chemical found inside comets. Okay, we're going to mix all these ingredients up inside our mixing bowl. And now we're ready to start adding the dry ice. And you can see here, we're starting to freeze all of this stuff inside our plastic bag. All right, and here we have our comet. And you can see, like a real comet, it's not particularly round. It's pretty lumpy and craggy and covered with dirt. So if we use this light to represent the sun, we can see what the effect of sunlight on our comet is going to have. And you can see what's happening is the warm light is starting to evaporate the gases. So as a comet travels around the sun, the heat from the sun starts to vaporize some of its volatile organic materials, and it starts to lose them in a long tail that can extend out very far beyond the comet.
In 1986, the Giotto spacecraft became the first mission to fly by a comet. It was Comet Halley, the only one known to return within our human lifetime, and that is also visible to the naked eye. The mission revealed that Halley is laden with several 100 trillion pounds of the molecule needed most by life on Earth: water. Based on this discovery and previous research, astronomers speculate that these icy bodies may hold clues to the source of water on Earth, and perhaps even life. Water. It blankets over 2/3 of Earth's surface. It nourishes plants and animal life, including man. But could this water have come from outer space? Initially, scientists thought that icy comets might have supplied most of Earth's water during the formation of our solar system. However, new research suggests that comets may not have been the primary source for our planet's water. Our Earth's oceans contain a combination of H2O, normal water, and HDO, or heavy water, which includes deuterium, a rare variety of hydrogen that has an extra neutron.
It turns out that the comets we've looked at so far, the deuterium to hydrogen ratio is about 2 times higher than that of Earth's oceans. So it isn't such a good match.
Scientists haven't completely ruled out comets. But could rocky asteroids have been a source of Earth's water?
The so-called carbonaceous chondrite types of asteroids, which are typically found in the outermost reaches of the main asteroid belt, have an almost exact match between their deuterium to hydrogen ratios and the Earth's oceans.
Carbonaceous chondrite asteroids may have less heavy water than comets due to the higher temperatures at which they were formed, since they're closer to the sun.
The main source of water is almost certainly near-Earth asteroids that have collided and given off large quantities of water vapor, which then, when conditions allowed, condensed as water on Earth.
Another possible source of Earth's water may have been identified with the discovery of 3 peculiar new objects in the asteroid belt.
Recently, scientists have discovered an exciting new category of object called the main belt comets. They look like a comet. They have a nucleus surrounded by a hazy coma with a long tail extending out. However, their orbital dynamics keep them entirely within the main asteroid belt. So from their orbital dynamics, they look like asteroids. Perhaps the origin of the Earth's oceans could be these main belt comets, which have high concentrations of water and other organic materials.
Scientists are still debating whether asteroids or comets could have delivered water to Earth. And the bigger mystery is whether they also could have delivered the essential elements for life.
Comets and asteroids both contain organic matter. They both repeatedly strike Earth. They certainly brought in organic matter. How much was dissolved in water and permitted the development of life? We don't know.
Over 70 kinds of amino acids have been found in meteorites. Many are the fundamental ingredients of proteins that make up living cells.
Recently, we found tiny little microscopic globules of hydrocarbons in a couple of meteorites. And these will be perfect precursors to cells. You imagine these things were falling on the Earth or anywhere else early in its history, providing ready-made little homes for organic reactions to occur in.
Another way to study whether cosmic rocks delivered water and possibly life to Earth is by collecting space dust. 100 tons of microscopic comet and asteroid material rains down on us every day. NASA's high-altitude aircraft program has been collecting uncontaminated cosmic dust grains in the stratosphere over 65,000 feet above Earth. The aircraft collects microscopic particles on silicon oil-coated sticky plate collectors on the wings.
It's a little like paraffin wax. So the planes are flying through the stratosphere. Here's a little particle slowly drifting down, and the plane just flies up and just smacks into this paraffin and it gets stuck there like a fly on a fly swatter.
These high-altitude experiments have revealed that interplanetary dust and the Earth are both made up of the same silicate grains that must have been present during the early solar system. So perhaps they help to deliver the building blocks for life. The high-altitude flights have prepared NASA to embark on one of its most ambitious missions. In 1981, scientists began researching how to collect actual pieces from a nearby comet named Wilt 2, which was traveling within the orbit of Mars.
The fundamental question we were trying to address for this mission was, did this comet, Wilt 2, ever have liquid water? We know it had lots of water ice, all comets do, but were they always cold? Or did they perhaps heat up inside to melt this water ice to liquid water? That's really important because once you have liquid water, then you can have things like life.
Scientists were faced with a daunting challenge.
Stage separation has occurred, and we have second stage ignition.
How could the spacecraft collect untainted pieces of a comet that would be moving 10 times as fast as a speeding bullet and therefore generating tremendous heat?
So imagine trying to stop a rifle bullet in mid-flight to study it without destroying the rifle bullet and without destroying you. How would you do that? That was our problem.
The solution was to use aerogel, a fragile porous substance made from silicon dioxide. Lighter than a cotton ball, aerogel contains thermal insulating properties that are stronger than window glass.
Hello, Peter. Welcome to Old Castle Glass. Glad you could make it.
NASA scientist Dr. Peter So discovered that aerogel could capture hot, fast-moving cometary particles with minimal damage.
The glass, what you see here, the heat insulating properties of aerogel more than 100 times better than glass, because glass is solid material. Aerogel mostly is air, so it doesn't conduct heat very well. So it's a better insulator. I have a piece of aerogel here, and I have some crayons. I'll put on top of this aerogel. So I'm going to use a torch to demonstrate that heating just a piece of aerogel will be able to insulate it so the crayon won't melt. It is burning, it's insulating it, and the crayon is still intact, it doesn't melt.
Aerogel may be a suitable thermal insulator on Earth, but would the substance hold up in space? On January 2, 2004, NASA's Stardust spacecraft met up with comet Wilt 2. Upon approaching its dust cloud, or coma, the craft flipped open a paddle-shaped collector tray containing ice cube-sized pieces of aerogel. The plan was to capture cometary particles moving at over 13,000 miles per hour. When the spacecraft finally returned to Earth, nervous excitement filled the air at Johnson Space Center.
I was the one to pick up the tray. In fact, when I pick up in there, I was a little bit scared. What if I pick up the tray, there's nothing there? I was broken in sweat.
Oh my God.
When I turned around and looked at it, wow, I saw about 36 particles. I could see we make it out.
It's amazing, amazing. Nice work. How you doing?
Further analysis of the Stardust samples may one day reveal whether Earth's water, or perhaps life, came from comets. But they've already provided insight into the striking similarities between asteroids and comets. Many particles contained abundant hydrocarbons that couldn't have formed in the cold environment where comets typically reside in the outer solar system.
We have the aerogel samples from the cometary tray. We mostly thought these grains would have formed out far from the sun where the comet formed. We find that some of the grains in the comet must have formed right up next to the sun's surface, heated to over 1,000 degrees, maybe 2,000 degrees.
After much analysis, scientists wondered, do some comets actually masquerade as asteroids? NASA's next mission would tackle that question head-on. Asteroids and comets, once thought to be very different cosmic bodies, may be more closely related than previously thought. In 2005, NASA's Deep Impact spacecraft launched a projectile into the nucleus of a comet named Tempel 1. For the first time, scientists captured images of a comet's icy, muddy interior.
We think that material that's underneath the comet's surface is really in a pristine state from when the comet was first formed, which could be billions of years ago.
The Deep Impact mission concluded that some comets actually mimic asteroids. After a comet orbits around the sun many times, it loses its icy, gaseous components. It essentially becomes dormant, showing a dry surface that resembles a carbonaceous chondrite asteroid, which contains many water-bearing minerals.
We're looking at meteorites now. which we always assumed always just came from asteroids, and wondering, which of these could have come from comets. What that tells us is that there are many different kinds of comets. They've all had different histories, just like asteroids have.
Asteroids and comets have much more in common than just physical and chemical composition. They've both left deep scars on Earth, which have resulted in the extermination of life, time and time again. Near-Earth objects are asteroids and comets whose orbits bring them close to Earth's orbit. In the case of asteroids, Jupiter's gravity or light pressure from the Sun can bump these cosmic relics out of the asteroid belt. Similarly, the gravity from planet Neptune can nudge comets out of the Kuiper belt. The scars from asteroid impacts can be seen throughout our solar system. All the terrestrial planets and moons show the marks of these deadly blows, including Earth. 65 million years ago, a cosmic object, roughly 6 miles across, impacted the Yucatan Peninsula near the modern village of Chicxulub, Mexico. It produced kinetic energy equivalent to 8 billion Hiroshima atomic bombs. The impact event left a crater in the ocean over 110 miles across and 20 times as deep as the Grand Canyon.
Because the impact event hit the sea simultaneously, this created tsunami-sized ripples that then crashed onto the shoreline of the Gulf of Mexico. The energy and the explosive ejection of that material from the crater was so dramatic that that molten debris actually blanketed all of North America. Life as we know it would have been virtually erased.
Many scientists now believe the impact event extinguished 75% of animal and plant species on land and sea, including the dinosaurs. Planetary geologist David Kring is one of the foremost experts on asteroid impact events.
We now understand that impact events aren't simply a geologic process that excavates a bowl-shaped cavity, but one that actually can affect the environment, whether it be local, regional, or global.
In 2001, Kring headed up the Chicxulub Scientific Drilling Project near the impact site in the Yucatan Peninsula. Kring's goal was to find evidence that the Chicxulub impact produced worldwide climate effects by drilling down to the rock dating to that time period.
The drilling project confirmed our suspicions that the impact event had collided with a series of very important rock types, limestone and anhydrite. The limestone, when vaporized, produced greenhouse-warming carbon dioxide, and the anhydrite, when vaporized, produced sulfuric acid rain. And so this confirmed some of the global climatic effects produced by the Chicxulub impact event.
The Chicxulub Scientific Drilling Project also revealed that the impact generated hydrothermal systems that span the entire diameter of the crater. These processes provided critical environments for new life to evolve.
The extinction of the dinosaurs and the other life that disappeared 65 million years ago created new environmental and ecological niches. So the survivors were able to evolve and take hold of those new opportunities. The subsequent evolution has led to the formation or the evolution of our own species, the human species.
The next Chicxulub-sized impact is estimated to occur 35 million years from now. But one can never be too certain when it comes to space rocks.
Unfortunately, these types of things do not occur like clockwork. In fact, the next Chicxulub-size impact event could occur tomorrow.
Many scientists are confident that a cosmic impact was responsible for wiping out the dinosaur. But they're still debating about what type of rock.
We aren't actually sure whether this was an impacting asteroid or an impacting comet, although the bulk of the evidence points towards an asteroid. Asteroids, in fact, dominate the flux of impacting debris to the Earth. Somewhere on the order of 85 to 95% of the objects that collide with the Earth come from the main asteroid belt.
If we do find a comet on an Earth-threatening trajectory, it could be difficult to deflect or destroy before it inflicts apocalyptic destruction. Near-Earth objects are asteroids that have been dislodged from the asteroid belt into Earth-crossing orbits and therefore could again one day strike our planet. Although most potentially hazardous objects are asteroids, comets remain a legitimate threat. These icy bodies, which come from the outer solar system, can travel 3 times faster than asteroids, so it only takes 9 months for them to get from the orbit of Jupiter to the orbit of Earth.
You couldn't plan years ahead for an impact from most comets. You'd hear about it maybe a few weeks ahead, maybe months at the most.
Fortunately, Jupiter acts as a planetary shield. It deflects or absorbs comets that drift towards Earth. And scientists now have the pictures to prove it. On July 22, 1994, telescopes around the world caught a glimpse of one of the most violent comet impacts in the history of humanity. A string of about 20 comet fragments named Shoemaker-Levy 9 crashed into the upper cloud decks of Jupiter at speeds 100 times faster than a speeding bullet. Since gaseous Jupiter doesn't have a solid surface, the objects were slowed down by its thick atmosphere and exploded as air bursts, which created plumes that were visible from Earth. At Sandia National Laboratories in Albuquerque, New Mexico, physicist Mark Boslow and his colleagues had predetermined that this cosmic spectacle would be seen from Earth through computer simulations.
People really did not expect this to be observable, partly because the location of the impacts were actually over the horizon, over the limb of Jupiter as viewed from the Earth. We simulated the interaction of the fragments with Jupiter's atmosphere at high velocity and the giant plume that was ejected out into space and could be seen rising over Jupiter's horizon as viewed from the Earth and from the Hubble Space Telescope.
Armed with new knowledge about airburst impacts, Boslow began reinvestigating a similar event that happened on our planet. On June 30th, 1908, the biggest cosmic disaster in recorded human history on Earth occurred in Russia. A large object exploded in Siberia's remote Tunguska wilderness. The blast ignited heat and shock waves, which toppled 80 million trees over an 800 square mile area. Yet no one was directly killed because few people lived in the area. The Tunguska disaster had baffled scientists for almost a century because no impact crater or meteorite has been found, and many of the trees in the area were flattened but not incinerated. Many scientists finally came to the conclusion that a space rock exploded as an airburst when it hit our atmosphere.
So this was an atmospheric explosion. It was really the only one we knew about, which made it seem unusual, very much like the Jupiter impact, and that in fact these are probably more common than we had really thought.
The asteroid was originally calculated to be 200 feet in diameter and released 10 to 15 megatons of energy based on the devastation in the area. But Boslow now thinks the size was much smaller.
When I did the simulation with a 15 megaton impactor, the fireball, the very hot gas that emerged from the explosion, descended all the way to the surface. That would have incinerated all the trees and created this zone of complete devastation that was not observed at Tunguska. The trees were not incinerated. Therefore, the mass would have had to have been less than people had previously thought.
Boslow designed new simulations to show that the momentum effect of the air blast, not the size of the rock, caused the devastation.
I modeled this as an object coming in at a 35-degree angle, and I exploded it when it descended below about 7 or 8 miles above the surface. It comes in, explodes, but the jet of hot material continues to descend. So what you see is the momentum effect after the explosion. The momentum is the velocity that continues to carry the mass downward before it finally slows down and stops.
Boslow's new simulations also account for the fact that the terrain was not flat, so the winds from the blast were amplified by the ridge lines.
But the gust is stronger on the top of the ridge, and just beyond the top of the ridge, that's where you would tend to have the most trees and the most damage.
Boslow's new research may mean that finding smaller asteroids is more important than previously thought.
One of the conclusions that results from this work is that smaller asteroids can create significant damage at the surface.
It's not a matter of if, but when we'll be hit by another Tunguska object. It's estimated to happen once every 500 years. And with Earth being more populated today, such an impact could be deadly. Asteroid and comet impacts are not events of the past. They're ongoing, and one day could again profoundly alter life on Earth. Believe it or not, Earth takes a hit from soccer ball-sized space rocks every day. Most go unseen. But in 1992, amateur video caught a meteorite flash across the nighttime sky. It eventually crushed the back end of a parked car in suburban New York. The odds of being struck by small or even large meteorites are extremely low, but the potential harm one could cause keeps NASA on high alert. Congress mandated that NASA must detect over 90% of near-Earth objects over a half-mile in diameter. These rocks could strike the Earth with the energy greater than all the nuclear weapons on our planet today. The most potentially hazardous near-Earth asteroid to date is Apophis, which is the size of a large city block. This space rock will make a close pass near Earth on April 13th, 2029.
Apophis has a 1 in about 45,000 chance of impacting the Earth. That is cause for at least some concern. Even though the probabilities are very low, it's not all that big as asteroids go, but if it were to fall on a city, it would obliterate the city.
It's still a minuscule probability, but it's not zero. I think a really good idea is to put a transponder on it that can be used to track it very accurately. Then we can know if it's a threat or not.
Scientists are developing mitigating technologies to either destroy a near-Earth asteroid like Apophis or nudge it out of harm's way. But as much as asteroids and comets are life-threatening, they also could one day be life-saving.
We also, with the same technology, have access to those asteroids for other purposes, such as mining them and retrieving materials to bring back to Earth.
Planetary scientist John Lewis has spent a career devising methods for mining space for precious resources. Lewis says asteroids' proximity to Earth present an opportunity to harvest their vast metal, mineral, and water ice for our planet, as well as future space missions and habitats.
I always envision the use of space resources to bring back to Earth. One of these is the extraction of water. The water can be used, of course, for life support. You can drink it. You can also generate electric power, stick electrodes in the water, electrolyze it into hydrogen and oxygen, and use the hydrogen and oxygen as rocket propellants for the return to Earth.
Among the many valuable components in asteroids is iron nickel, as well as highly priced metals such as cobalt and platinum. These could be extracted to construct a variety of things on Earth. Lewis says engineers could build Earth-orbiting processing plants in space to carry on mining manufacturing as well as energy production.
My concept is that a lot of these structural materials could be used in the process of putting up solar power satellites to produce unlimited quantities of cheap electricity very cleanly. So we produce this power, beam it down to Earth.
And landing on an asteroid is not complete science fiction. In 2001, the Near-Earth Asteroid Rendezvous mission, known as NEAR, became the